if you burn paper, it becomes ash. Okay, you cannot convert that ash into that paper. Or if you boil egg, the boiled egg cannot come into that raw egg, right? So what is happening? So let's write the definition. So what is a spontaneous process? Spontaneous process. Spontaneous is the English word. Spontaneous means like it just happened by itself, right? Hello.
Yes, sir.
Hmm. So tendency of a process of a process which go into into a particular direction. So what we mean by it? Like for example, melting of ice. Simple. Melting of ice. Do you have to work on it to melt an ice?
No, sir.
But if you want to, you have to make some ice from water. What do you have to do? You have to put that put that water in fridge so that it become ice. So here, who is working on it? Yeah, which energy is going into the to melt to freeze that ice? Electrical energy. The fridge is what fridge is doing? The refrigerator. It is freezing the ice. So energy is wasting on it. It is not happening spontaneously, right?
Yes, sir.
Yes.
So that is not a spontaneous process. That is non-spontaneous process. Means we have to work on it. Got it?
Yes, sir.
Like evaporation of water. Can anybody tell at what temperature evaporation of water take place?
100 degrees Celsius.
100 degrees Celsius.
Anyone else with different answer? You can say it, no problem. If you have any other answer. Okay, I think the class is with 100 degrees Celsius, but no, the evaporation of water takes place at every temperature. Like for example, uh, put some water in any cup, okay, and leave it for 2 days. The level of water will reduce. Have anybody observed? Or if you have some tea left in your cup, after if you leave it for some hours, the water is lesser there. Have anybody observed this? That
Yes.
somehow the level of water is not there, or some way it has been dried out. So the temperature is not 100 degree, right?
Yes, sir.
So it actually evaporation of water takes place at every temperature. However, at 100 degrees Celsius, the evaporation of water is very abrupt. Actually, there is every molecule of water has the tendency to evaporate. But in this condition, just for your knowledge. And this in any beaker or any vessel, water is there. Only the surface water has the tendency to evaporate, right? So only this is the difference. So at every temperature, at at 0 degree ice also, 0 degree water also, zero at 0 degree there is water also, there is ice also. You may have learned in this enthalpy topic and earlier topics. At 0 degree Celsius, you have uh, ice also and water also. You know it before. Hello.
Yes.
Students, be responsive in the class, okay? Otherwise I will understand that you understood. Okay, so like for example, 0 degree you may have not feel this. Let's give you an example of 100 degree water. 100 degree boiling water is at water phase also, some water is at water phase also, and some 100 degree water is in vapor phase also. Okay, that boiling water, the whole water, the water in the vessel is at 100 degrees Celsius. Some are in vapor phase, some are in water phase. Okay, so what is the difference? That is latent heat of vaporization. You have heard this term, latent heat of vaporization.
No, sir.
No, sir.
Anybody? Latent heat of vaporization. Okay, no problem. This was in actually ninth class, and you will study this in later topics. Don't worry. So this latent heat of vaporization, if you add some more heat into the 100 degrees Celsius of water, it vaporizes actually. Okay. So at 100 degrees Celsius, we have water also, and we have water vapor also. Okay. Don't be confused that, oh my god, what is happening at 100 degrees, means at this temperature, how both are existing. Actually both are existing. Like in this 0 degrees Celsius, ice is also existing, water is also existing. But if you extract more heat from here, it will become water, and that heat is called latent heat of fusion. Just for the sake of knowledge, 0 degrees Celsius, ice and water both are present, and at 100 degrees Celsius, water vapor and water both are present. Okay.
Yes, sir.
For this latent heat of vaporization and fusion, we will study in later chapters. Don't worry. We will see this numericals also. So so spontaneous process, the tendency of a process which go in a particular direction by itself. This is important. By itself. By itself. Okay. or or by little push. By little push. So what is the example of this? What is meant by little push? Actually, for example, there is also a spontaneous process, that if you take hydrogen plus oxygen, it will become water. Okay. Can anybody tell me what we are doing here? uh, what is the uh, catalyst, or how these reactions happen, that if you mix hydrogen with oxygen, it will become water? Anyone? Let me tell you, if you mix hydrogen with oxygen directly, nothing will happen except we do something. What we do here? Electric discharge. Electric discharge. If we put some electric discharge in it, put some electric spark there with hydrogen and oxygen, it will become H2O. Got my point?
Yes, sir.
Yes.
So here the little push is electric discharge. We are not going to bring H2 and oxygen come in a, for example, in a container. No, after electric discharge, it readily converts into H2O. Got it?
Yes, sir.
Yes, sir.
You can view in this YouTube also, how H2 and O2 are reacting. There are some videos in a balloon. They have mixed H2 and O2. Okay, and they have put some electric discharge there. So after that spark, the uh, you know uh, this thing, H2O becomes, and the balloon gets, like them, like deflated, right? Because H2O is in liquid form, so, and this is in gaseous form, so there is no volume. Liquid is no volume, right? Liquid has very lesser volume, means negligible volume with respect to gas. Got my point?
Yes.
Yes,
Hmm.
sir.
Like if you take 1 ml of, for example, uh, 1 ml of any perfume, any ether, okay, and you heat it up, it will, go into the whole room. It will fill up the whole room, right? So
Yes, sir.
1 ml is filling up the whole big room. So there is very huge difference between the volume of gas with respect to volume of liquid. If you will see the experiment, you will love it. So you understood the spontaneous thing?
Yes, sir.
Hmm.
Yes, sir.
So, so, so now we will move on to what is non-spontaneous process, which has tendency to not not to go in any reaction or any process, except giving very huge amount of energy or very huge amount of process, like for example refrigerator, right? Or for example, if you have to pull up, we have motor in our house, so that water get comes and fill up in the tank, right? Got my point? So which
Yes, sir.
energy,
Yes, sir.
we are using? Yeah, which energy is getting exhausted?
Electrical energy.
Yes, sir.
Electrical energy. Good. Okay, good. So spontaneous process. You got my point. So what are the limitations of first law of thermo? So what are the limitations of first law of thermo? So limitation of first law of first is, it doesn't tell about feasibility of process. For example, if you want to convert graphite into diamond, artificial diamonds are also made
Yes, sir.
from graphite. So this first law of thermodynamics will not tell that how to convert graphite into diamond, right? Because it is not feasible. You have to give very high amount of pressure and temperature, then only it would convert into graphite into diamond, right? Secondly, uh, direction of the process. Okay. So till here you understood? Hello?
Yes, sir.
Till here you got the you understood the topics?
Yes, sir.
Yeah.
Hmm. Okay, good. So we will introduce a new term which is known as entropy, and entropy is related with this only. Then we will understand the final second law of thermodynamics. So the topic is entropy. Entropy is very interesting term. There is a lot of question comes with entropy, and this is very easy also, easy to understand, and there are very easy numericals. So what is entropy? Entropy will tell you ki how much randomness is present in the system, or how much system is disordered. For example, if you first tell me, the molecules of liquid is you know is disordered, or molecules of gas, more which one is more disordered, or randomness is present in gas or
Gas.
liquid? Gas.
Gas.
Good. So we will say here that entropy of gas is larger than entropy of liquid, right?
Yes, sir.
So what is the definition of entropy? Entropy is degree of randomness. We will see several examples with practical example. You will understand that yes, entropy is increasing. Like for example, we have gas in a 10-liter container, and we have also gas in 100-liter container. So where will be the randomness will be more? Where the molecule will be more disordered? In the smaller container or in the larger container?
Larger.
Uh,
Larger container.
larger container. Good. So the entropy is degree of randomness or disorderness of the system. Got it?
Yes, sir.
So as disorderness increases, entropy increases. Good. Mathematically, we have formula for it. Mathematically, we have formula which is it is denoted by delta S. Okay. Mathematically, it is delta S is equal to Q by T. T is temperature here, and Q is heat involved in it. Okay. For example, let me also tell you that this entropy is a state function. Who will tell me what is state function? Anybody remember from first or second class? Hello.
Yes, sir.
So state function, you may have remember that state function is are the units which is defined at that state only. For example, uh, you have internal energy. Internal energy denoted by U is a state function. At a particular time, you can say that this is the internal energy of the system. Do you remember? Okay, nobody remembers. Now listen. Okay, no problem. Hello.
Yes, sir.
If nobody remembers what is the state function, no problem. Just hear me out. Okay. So state function is a it it is defined as a particular time without any, at a particular time you can say that this is the thing. Like for example, a, a system is present. Okay. You can at a particular time you can say what is the pressure of it, what is the volume of it, what is the temperature of it, right? Tell me. Hello.
Yes, sir.
Please be responsive, everybody. I think I'm hearing out only 2-3 person names. uh, Nobody else is responding that much. And we have hmm, yeah, I think it's 7 people. So state function is measurable properties like temperature, pressure, and volume, right? You can say na, that this is the temperature of the system.
Yes, sir.
So these are the state functions. And what are the path functions? Oh, see, you have to remember these things because the first or second class of any topic is very important. In every every chapter they are going to be used in each class. So try to remember those points. Okay. And these are important things also, not like you can leave it and just move on. Okay. So there are state functions, and there are some variable path functions. Path functions. Okay. There are some state variables. We have bifurcated in these two parts. You can take out your past notes, and also you can revise them. So state functions are like volume, temperature, pressure. I don't think that you may have doubt in this thing that you cannot take out the any uh, state's volume or temperature or pressure. That's very easy na. At any time you can take out what is the volume of the system, what is the temperature of the system, what is the pressure of the system, right?
Yes, yes, sir.
Ha.
Yes, sir.
So little problem comes when what is the path function. The path function depends upon the initial and final state of the system. What do we mean? Like work, like for example heat or work. When we give for example 20 kilojoule of to the system. Okay. Just imagine it with your practical knowledge. For example, in a in a vessel or in a container, you are giving 20 kilojoule, right? It has like any substance, it has water in it. Okay. You have given 20 kilojoule of heat by a burner, right? Hello.
Yes, sir.
So it may have took some time now, like 5 seconds, 10 seconds, 10 minutes, right?
Yes, sir.
So there is some time in it. So you cannot give instantly that like 10, I have given you 10 kilojoule. That is not possible. So this is a path function, that it takes some path, it takes some process. And similar is the term work. How? Like for example, you have a piston, you have pushed that piston, so you took some time to push it up, right?
Yes, sir.
Can you see? You have took time. So this is the work done. You cannot say at a particular time stop the clock and say that I have worked. I am doing this work at this time. There is a certain time, like 5 seconds, 10 seconds, 10 minutes, and you have worked out through this time. But at in the time with respect to volume, temperature, and pressure, you can say that at exactly at this time, at this moment of time, this is the volume of the container, This is the temperature of the container. This is the pressure of the container. This is the internal energy of the container. Now you understood?
Yes, sir.
Yes, sir.
So this entropy, this randomness is also a state function. Like at a particular time, you can say that uh, these molecules in this container or in this system, they are, have this randomness in it. Okay. Okay.
Okay, sir.
Yes, sir.
Some people are not responding in, either I'm asking some question with, any formula, anything. So let's proceed. Acha, one thing more. Uh, e- Extensive function and intensive function. Anybody remember? Hmm? This is the, you have learned this in first class. Extensive property, intensive property. Anybody? Anybody remember what is intensive property? What is extensive property?
Extensive
Extensive property depends on the amount or mass of substance,
Hmm?
and intensive does not depend on the amount or mass of substance.
Okay. Anybody with another definition or with another understanding? Ali Muhammad. Ali Muhammad, can you
Sir,
hear
it
me?
doesn't depend upon mass.
Okay, can you give some example? Any example?
Sir,
Intensive or
volume.
extensive? Volume is with intensive or extensive?
Sir, intensive.
Volume is with
Extensive, sir.
how? Anybody can anybody explain how volume is extensive?
Because volume depends on the mass of substance.
Okay, okay, okay. Let's give me. I will give you an example, and you will always remember. Okay, to find out what is extensive and what is intensive. If you get confused, because you may remember the definition, but you may get confused. Like for example, I was about volume. Okay, take a container with you. You don't have to take a container, just draw a container. Okay, and fill it. Now, for example, first very basic example is mass. Mass is an extensive or intensive? Wait, geobita. Hello.
Yes.
Mass is intensive or extensive?
Intensive.
Intensive.
Extensive.
Extensive. Good. So mass is extensive because by definition also uh, we are saying that mass dependent property. So just for example, if you got confused, just cut this container into half. Okay. Have you sliced this container into half?
Yes, sir.
Good. So does mass becomes half? If you are giving taking this example, if does mass also becomes half?
Yes, sir.
Good. Does
Yes,
volume
sir.
becomes half?
Yes, sir.
Yes,
Uh,
sir.
Zainab,
Yes, sir.
does if we take talk about moles, does moles also become half or do not, doesn't it doesn't become?
It doesn't become half.
No, moles also becomes half. How? See, if you cut this container into half, also half number of moles come in this part and half number of moles come in this part, right? Got my point?
Yes, sir.
Hmm. You people remember what is internal energy? No problem. Internal energy is also becomes half. Okay, it is temperature dependent and it is also dependent on the number of molecules you have. So the temperature, the molecules also reduced, mass reduced, so internal energy also reduced, right? Okay.
Yes, sir.
Yes, sir.
Now Shaima, tell me, does density becomes half?
No.
Shaima, no. Good. So density will remain density only, because density of a substance does not depend on mass. That's another thing. But if you take an example, if we have some water here or some oil here or some halwa here, something anything, the density does not changes if we divide, right? If we have big container of ice cream, if you take one scoop of ice cream from there, the density does not changes, right?
Yes, sir.
Ah.
Yes, sir.
uh, Temperature, Jesseline, tell me, does temperature becomes T by 2? Does temperature also reduces or temperature remains same?
Reduces.
If you have big container of ice cream with you, and if you take out one scoop of ice cream, okay, so its temperature decreases or increases or remains same at the moment of time when you scooped out the ice cream?
It remains same.
Same. Good. uh, Everybody understood?
Yes, sir.
uh, when you learn with examples you will remember through longer time. However, in that case also you have to revise. Okay, otherwise you will get confused what is intensive, what is extensive. Okay, you people remember molarity?
Yes, sir.
So what do you think, molarity is intensive or extensive? Don't worry, it also does not affect. Okay, see, do you anybody remember molarity formula?
Number of moles by mass in kg.
That is molality. The you have you are little wrong. That is molality, small m. This is molarity, number of moles upon volume of solution. That is number of moles upon uh, mass of solvent in kg. Okay, so you will see that number of moles also reduced to half and volume also reduced to half. So it will become n by v only, right? So molarity also does not changes. Okay,
Yes, sir.
Abir, Adil, can you hear me?
Yes, sir.
I think you were responding, right?
Yes, sir.
Uh, Shabi Sabiha,
Yes, sir.
uh, tell me, does freezing temperature decreases or increases? Freezing temperature or boiling temperature, if you cut this solution into half, what do you think? Let's give you example with ice cream only. if you take out one scoop of ice cream, okay, from a spoon, so what do you think, the temperature with which it will melt, and the temperature which the ice cream wasn't present in that container, will there will be a difference,
It
or
will decrease.
the melting temperature? Let's for example assume that it will melt at 0 degrees Celsius. Let's assume that it is, melting at 0 degrees Celsius, and you take out one scoop of it. So will it melt at 0 degrees Celsius, or 1 degree Celsius, or minus 1 degree Celsius? Shaima, you tell.
So it remains same.
It remains same. It will not affect actually, because it is a property of that substance. It will not affect, so it will remain same only, right? Why does it melt in scoop first? I think she was having doubt, because actually um, when you take out that scoop out of that container, it it has contact with room temperature very very earlier. However, in that container, the temperature is not temperature will be same. However, the room temperature is not affecting it. So melting point of that ice cream is same. Okay.
Yes, sir.
So many things will be same. We don't have to go in detail like pH. Okay. Like viscosity and all. Okay. Like for example, you have a good big container of honey with you, and you have one spoon of honey. Both will have same viscosity, right?
Yes, sir.
So I think intensive or extensive property is properly clear to you.
Yes, sir. It's clear.
Don't ever forget this. These are small terms. However, this is very important. Okay. Hello.
Yes, sir.
Hmm. Okay. Good. Hmm. So where were we? This entropy. Okay. So entropy, you understood the degree of randomness. Okay. The more randomness, more will be the entropy, right?
Yes, sir.
Hmm. Okay. For example, the same example we will take. Now we will take like H2 plus N2 gives NH3. We will balance it out. So I think is it balanced?
Yes, sir.
Yes.
So see, we have 3 moles of hydrogen with us and 1 mole of nitrogen with us, right?
Yes, sir.
Yes, sir.
So we have 4 moles of gas.
Yes, sir.
Acha, all are gases. I think there will be no confusion regarding it, right?
Yes, sir.
Yes, sir.
So we have 2 moles of ammonia with us. Okay. So tell me, uh, can means try giving me answer that the randomness has increased or decreased?
Decreased.
Decreased.
Yeah, decreased. You all are correct, because we have 4 mole of gases are here. Here the molecules are flying here and there. The degree of randomness is very high, and here only 2 mole of gas is present, right?
Yes, sir.
You can understand we have in reactant position, we have 4 children. Okay, and they are very they are naughty children, so they are very random, they are like playing here and there. Okay, and after some process, only 2 children left. We took out 2 children. Okay, so finally the randomness will become lesser, right?
Yes, sir.
Good. So everybody understood?
Yes, sir.
Yes.
Let's take another example. So tell me, here entropy increased or decreased?
Decreased.
Increased.
Wait, let me ask. Jesslyn,
Yes, sir.
according to you, did entropy increased or decreased? Just replace the entropy word with randomness. Does randomness increased or decreased?
It decreased.
Okay. Ali Muhammad?
Decrease.
Hmm?
Decrease.
The randomness of the molecule of H2O, did it increased or decreased? What do you think?
Sir, it is the same.
Remain same.
Yes, sir.
Let me tell you all that the randomness means this the molecules, look into the molecules, they are maybe vibrating more, or they are traveling more. So in solid, the molecules are bonded. Acha, anybody got confused that H2O and I have written in bracket solid? What is it actually? Can anybody guess?
Ice.
Ice, simple. H2O in solid form is called ice,
Ice.
right?
Yes, sir.
Uh, if anybody got any confusion, you can ask. There is no issue. Okay, so that we can proceed. So H2O solid is ice, and ice is converted into water. Okay, so here entropy has been increased. How? Because in solid form, any molecules in solid form is in is less vibrating, is less delocalizing, right? And in liquid form, the water is more vibrating, intermolecular space is larger, intermolecular forces is lesser, right?
Yes, sir.
So you all remember the point,
Yes, sir.
how entropy increased. Ali Muhammad, you understood?
Yes, sir.
Good. So these are the major things, this entropy thing. So you have to find here delta ng. Have you used this term delta ng? Anybody? No problem. It's called change in moles. N is moles, right?
Yes, sir.
Change in moles of gas. Okay. And when the state changes from solid to liquid to gas, entropy will always increase, right?
Yes, sir.
Uh, Now we will take an example. You will understand. Abir, can you tell me delta S entropy has increased or decreased?
Sir, could you repeat the question?
In this question, see the
Yes, sir.
question I have written. Entropy has increased or decreased?
Increased.
Increased. Dry, what is dry ice?
CO2.
CO2,
Solid
CO2,
form.
solid form, right. CO2 in solid form is called dry ice, right?
Yes, sir.
Yes, sir.
Hmm. Okay. There are some other examples also. So this one is first example. This one is second example. Some other example like if you mix gases, deltas will increase. Okay. Some unique example like, for example, can anybody comment on this? That whose entropy will be greater, graphite or diamond? Anybody?
Graphite.
Graphite.
Why?
Good. Why?
So diamond is the hardest substance, so it will have less randomness.
Somewhat true. Any other point?
Graphite is brittle and can be broken down easily, unlike diamond.
No, diamond is brittle. Graphite is not brittle. Okay, see. Uh, Anybody remember that diamond structure is like this, tetrahedral? Okay. No, diamond structure is like this, right? And graphite is like this. In sheets.
Yes, sir.
So graphite is used in lubricants, right? So the layers of that are slide each over each other. Okay. So here the carbon atoms of the diamond are bonded with each other. They cannot move. However, in graphite, they readily moves, right? So the more the movement, more the randomness, more the entropy. Okay. Let me repeat. More the movement, more will be the randomness, more will be the entropy. Got it?
Yes, sir.
Hmm. Good. So, so here the theory is clear.
Yes, sir.
Yes, sir.
Good. So, till here, anybody, any question?
Sir, in the equation Q by temperature, what does Q stand for?
Q is the Q is the heat. Here Q
Okay.
is Q reversible. We will take several numericals. Don't worry. Q reversible. Q in thermodynamics, always remember there is heat involved. Okay.
Okay, sir.
However, if you will get H or U, there are some. They are also heat, but U is at constant temperature, and H is at constant pressure, right? Enthalpy. The heat exchange at constant pressure is called enthalpy, right?
Yes, sir.
Another great example. Try to answer this. You will means you can logically answer all these things. You don't have to, mug up these, right? However, you have to mug up those formulas, but the theory thing, are you getting feeling of that? Hello? Hello?
Yes, sir.
Are you
Yes, sir.
getting this point that how this randomness is increasing?
Yes, sir.
Yes, sir.
Yes, sir.
So let's take an example. Like for example, we have nitrogen gas, and here also we have nitrogen gas. So where is the difference? We have taken this at 4 atm pressure, and we have taken this at 2 atm pressure. So in this process, we have decreased the pressure of the container in which nitrogen is present, right? Have you understood the question?
Yes, sir.
The most important thing is to understand the question, then only you can understand the answer. So try to understand the question that in this we have a container, we have nitrogen in this. First we have high pressure, 4 is greater than 2. We have high pressure and we have decreased the pressure, right? We have decreased the pressure. Okay, so I'm asking that the randomness has increased or decreased.
Increased.
Increased. Increased.
Everybody got correct answer. Why? As the pressure decreased,
Less pressure.
less pressure, the molecules have got more space to, to take to go here and there, and thus randomness increased. Simple, right?
Yes, sir.
Ali Mohammed, say something.
Yes, sir.
You understood the point or not?
Yes, sir. I understood.
Understood the point. Good. So let me ask you next question. We have iron here in solid form, and we have iron here in solid form. Okay, and we have put this iron at 300 Kelvin, and we have put this iron at 500 Kelvin. Okay, are you listening? Ali, are you there?
Yes, sir.
So tell me, does the what happened? Uh, Entropy is increasing or decreasing?
Decreasing, sir.
Hmm?
Decreasing.
Tell me, if we heat up any substance, okay, solid, liquid, or gas, just hear me out. Okay, understand this. If we heat up any substance, solid, liquid, or gas, the molecules got more randomness, more energy, more vibration, or is it or it decreases?
Sir, the randomness increases.
So by increasing temperature, vibration or increases or decreases?
Increases.
Increases. Simple. As you increase temperature, the molecules got more energy, right? So
Yes, sir.
it starts vibrating, it starts moving here and there, so randomness will increase, so entropy will
Increase.
increase. Simple. Everybody got the point?
Yes, sir.
Yes, sir.
Yes, sir.
Good. Now so I think you have understood that what are the factors which factor affecting entropy, right?
Yes, sir.
So there are many factors which affect entropy, like temperature, pressure, number of moles, what is happening, or phase change. So all we have gone through the topics. Anyone with any doubt in this 6 point? I can repeat today. No problem with that.
Sir, the last one, can you explain again?
No problem. Anyone else?
So can you explain the fourth one?
Fourth one. Okay. Anyone else with another problem? So see the fourth one. What we talk about, randomness or more movement or more vibration, right? In entropy thing. Hello.
Yes, sir.
So where is the movement between molecules, in diamond or in graphite? Movement between molecules. Possible movement between molecules.
Graphite.
Graphite. Acha, do you know how there is movement between graphite, or you are just saying that means to, just saying? You have the understanding of this? Anybody? How graphites are, what I'm saying? How graphites have can molecules move with the other particles? Anybody? Nobody? You should have told earlier now. I thought that this one is from class 8 actually. See, no problem. I can repeat here. There is no issue with me repeating. If you will not tell that where is the issue, how will I understand? See, these are graphite molecules. These are carbon atoms, okay, and they are making bonds. You have had this na chemical bonding.
Yes, sir. Chemical.
So this is covalent bond, okay, carbon carbon covalent bond, okay.
Yes, sir.
So we have this thing. So these are carbon carbon atoms. They are bonded together in this fashion, okay.
Yes, sir.
And we have sheets of this thing. We have sheets of this these structures. So all these structures are bonded together with some weak forces known as van der Waals forces. Anybody heard this term earlier? Van der Waals forces.
Yes, sir.
Yes, sir.
So I think you may have heard that these sheets of carbon structures are bonded together by van der Waals forces, where they are very weak forces. So what happens? What happens actually, that these slide, these sheets of carbon slide over each other like this. Like we have this many hexagonal shaped carbons, and we have many hexagonal shaped carbon here. So they slide over each other like this. Got my point? Why?
Yes,
How they will not why they are sliding? Because they are bonded by weak forces. So nobody is holding forces with much force. So after applying pressure, they get slided, right?
Yes, sir.
Yes, sir.
So there is movement. Movement means randomness. Randomness means there is entropy increase, increment in entropy. Okay.
Yes, sir.
And in the diamond thing, every carbon atom is bonded very means strongly. Okay, very strongly in tetrahedral fashion. Okay, so they are not going to do anybody. They are not leaving any carbon atom out of its place. So they are fixed. So there is no entropy, zero entropy. Okay.
Yes, sir.
Graphite is used in pencils. You may have written with pencils. So when you take out the pencil and rub it, you will see like if there is some lubricant.
Yes, sir.
So this is because of the graphite present in the carbon lead, right? So actually these layers are sliding over each other. So uh, this is the presence of, because this is the presence of graphite. Graphite is used as solid lubricant. Lubricant, you understand lubricant, everybody?
Yes, sir.
Yes.
Yes, sir.
Lubricant which used to reduce friction. So there is we use oil to reduce friction in machinery, and grease, oil. But in some machines we have to use solid lubricants. So graphite is used as solid lubricants because of these structures. Okay, so I think you have understood the this thing. Who have asked this question?
Yes, sir.
Okay, so this one, iron thing. See, as temperature increases, now, the vibration, the vibrating molecules increases. Acha, do you have problem with this step? Vibrating molecules increases,
No, sir.
or you can say vibration increases. Okay, so as vibration increases, randomness increases. Simple. Got my point?
Yes,
As
sir.
vibration, see, for example, this is this pen, this was vibrating this much. Now after hitting this is vibrating here and there, right? Here and there. So randomness has increased, right?
Yes, sir.
So I think you all have understood. Okay.
Yes.
Yes, sir.
Good. Now we will go through some calculation, entropy calculation, some mathematical thing, and some numerical thing. I think all have understood the theory part. Everybody.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Understood, sir.
Entropy calculation. So the first formula is delta S of universe is equal to delta S of system plus surrounding. This is simple. The universe which has a system and its surrounding, if you will add both those entropy, you will get entropy of the universe, right? Hello.
Yes, sir.
This is a simple formula. Okay. Mathematical formula we have already written. Okay. So now we will get into derivation. So we are going to derive what is the change in entropy in isothermal process or isochoric process or isobaric process. Okay.
Yes, sir.
So Q is equal to U plus W. The first law of thermodynamics.
Yes, sir.
So please be responsive. So we are there is some entropy change. There we are doing some process. So we are using delta. Okay. Delta Q is equal to. Acha, you understand this delta or D difference? If you write delta Q or DQ, what is the difference? Anybody? Hmm. Okay, no problem. See, delta is large when there is large difference. Okay, large difference, and DQ is small difference. Okay.
Yes, sir.
Actually, these are Greek letters, so we are using in that fashion only. Okay. So we are going through a small thing and then we will integrate like in physics we always do. Okay. So dq is equal to du plus dw, internal energy change and work change. So we will divide it all by uh, temperature. Why? Because dq by t is entropy. Huh. So I don't think you have problem with that till now.
No, sir.
Wait. So where from where we have written this formula, the first formula, this dq is equal to du plus dw.
From first law of thermodynamics.
Ah, good. So kindly relate all those things which we study. Okay. uh, Otherwise you will have this much amount of burden that I have lot of formulas, where is the derivation, where to start, where to end. Okay.
Yes, sir.
Hmm. So U is NCVDT, right?
Yes, sir.
You may have remember the formula. See, the major formula, you try to remember them always. You don't try to forget them. Okay. Always remember the
Yes,
formula,
sir.
the major formulas. You may forget some formulas, but the du formula or like pv is equal to nrt, you don't have if you will forget this formula, then it will be very um, drastic catastrophic to your study. So du by dt, so we will change it ncv dt. Okay. And here we will be dw is pdv. This is also a formula. Okay. And we will you know integrate it. We will integrate it from t1 to t2. Okay. So n will not change with respect to temperature. Cv will also do not change with respect to temperature, right?
Yes, sir.
Hmm.
Yes, sir.
So we will have this term. Acha, this thing PV is equal to nRT. We will write here PV is equal to nRT. So P by T is nR by V, right? So we will replace P by T by nR by V, and here there is dV, and we are integrating it. So dt by T is ln T. Do you remember this thing? And here also n is constant, R is universal constant, and we will get ln V, right? Hello.
Yes, sir.
So finally we will get NCV ln T2 upon T1. Actually we will get ln T2 minus ln T1. By mathematical calculation we can write ln T2 upon T1. Okay.
Yes, sir.
You remember na ln A minus ln B is equal to ln A by B. Okay. This is a mathematical thing. You don't have to worry. Just go with the flow. ln V2 by V1. That is it. Okay. Okay.
Okay, sir.
This was dq by t, and finally dq by t is delta s. So this is the main formula. So just try to remember this formula. Now, if you want to say about isochoric presses, we will go through some processes. Like for example, first we will take isothermal process. For isothermal process, in isothermal process, what is same temperature, pressure, or volume?
Temperature.
Temperature. Good. So in isothermal process, T2 and T1 become equal, right?
Yes, sir.
Yes, sir.
So T2 by T1, it will cancel out and it will become 1. ln1 is ln1 is, I'm writing here, ln1 is equal to 0, or log 1 base anything is 0. Okay.
Yes, sir.
Let me give you an example. If you take x and here is 1 and here is you know, if you will put 0 only, anything power of this is 1 only, right? X ki power 0 is 1 na.
Yes, sir.
So this is the thing. In ln means what? Log base e, right? Hello. Are you means do you have no interest with maths? Hello, hello, hello. Hello.
Yes.
Yes, sir.
We are completing the class. Don't worry that this class is going to end. Just be with me. Okay. So delta s is this will cancel out, and we will the final answer will be nr ln v2 by v1. Okay.
Yes, sir.
See how I have written this. At PV is equal to nRT when temperature is constant. Okay. So P1 V1 will become equal to P2 V2. Right?
Yes, sir.
So P1 upon P2 is equal to V2 upon V1. So from here we have put this. Sorry. From here we have put this and this formula comes. Okay. We don't have to remember each and every formula. We have to remember this formula. If you will remember this formula, you will see, oh, this is isothermal process, means temperature is not changing, means T2 will cancel out T1, right?
Yes, sir.
So this will cancel out, then whole this will become zero. Are you getting my point?
Yes, sir.
Yes, sir.
I don't think everybody is getting this. Tell me who is not understanding this. Ask me, I will, repeat this. There is no problem. Hello. Anybody which is not understanding this, uh, you know, mathematical calculation?
No, sir.
See. Mm, in this thing, I have cancelled out this. This is becoming 1. So this is all becoming 0. You have to understand ln. I have written here ln1 is 0. So here it is becoming ln1. This is becoming 0. So finally delta is becoming ln nr ln v2 by v1. Got my point?
Yes, sir.
Yes, sir.
Good. Now for acha, you can I think you all can directly say for, tell me, for isochoric process. What happens in isochoric process? What is same? Temperature, pressure, or volume in isochoric process?
Volume.
Volume, simple. Volumes remain same. I will give you, a trick to remember, a logical trick. Volume same. See, the other process is isobaric process, right?
Yes, sir.
So in isobaric process, actually, you know, uh, mm, barometer is used to measure pressure, or in bar pressure is measured, right? In
Yes,
bar
sir.
pressure so isobaric pressure is known as where pressure is same, right? Simple. Now
Yes, sir.
tell me, uh, don't tell me, I'm writing here again. So what is the what we will cancel here?
Volume.
Here the volume is same, right?
Yes, sir.
So this will cancel out. This will cancel out 1. this nr ln1, this will become 0. So we will finally we will get delta S is equal to ncv ln T2 by T1, right?
Yes, sir.
So you don't have to remember each and every formula. You got my point?
Yes, sir.
And finally we have isobaric process, right?
Yes, sir.
And this is the last thing. We will be good for today. Isobaric process. What is same here?
Pressure.
Pressure. Pressure same. Okay. So here the pressure is same. So here what we will do, delta S is equal to, here CV will not come, CV will come CP. Why? CV is at constant volume and here the pressure is constant. So here CP will come. Okay.
Yes.
NCP ln T2 by T1. And see what the other thing was, NR ln V2 by V1, which will get cancelled out. See, we have other NR ln P2 by P1 is also there. Okay, so this one cancel out and this will be the final answer. So you don't have to remember each and every formula. Okay. See, you have to remember this formula, Army. For isothermal process, this will become 0. This will be the final answer. Okay, this will be the final answer. In choric process, this will become 0 and this will be the final answer, right? Getting my point?
Yes, sir.
And in the isobaric process, only this will become CP and this will become 0. So overall, you don't have to learn 3 formulas. You have to learn only one formula and just relate with it. Okay. Have you understood?
Yes, sir.
And finally, this one is this one is very very easy. For this one, I am putting it at a star. For adiabatic process. In adiabatic process, what is 0? What is same? Sorry, what is same? What is same in adiabatic process? Heat exchange. Heat is not taken or given. Do you remember? In adiabatic process? Hello? Anybody? Shaima? Zainab?
Yes, sir.
Yes, sir.
So, okay, you may have forgotten that what is this process, but after I'm saying what is adiabatic process, the where heat exchange is 0. Now you remember.
Yes, sir.
Yes, sir.
So no problem. Actually, problem is there. You should have revised it, but it's okay. So for adiabatics, the heat is not neither taken or given. There is no heat exchange, right?
Yes, sir.
So dq is 0. There is no heat given or received. So delta S will become, since delta is dq by t, so this will become 0. Got my point?
Yes, sir.
So you don't have to
Yes,
do
sir.
anything here. Here the entropy change is 0. Okay. So you understood all these points?
Yes, sir.
Yes,
Yes,
sir.
sir.
Isothermal process, the class has been just is ended. I'm not going to start any other topic. I'm just going to uh, take your moment that we have understood what the entropy is, and in the last process we have understood what is the formulas. We have derived it, and we have learned this formula only. And after this, see, actually now when you go through these logics now, you will remember, acha, what is isothermal is temperature is not changing. What is isochoric? Oh, volume is not changing. What is